Hello, my name is Hao-Yu Wang from the Young Scholar Program. This is my project on the photocatalytic degradation of organic contaminants in produced water. So for an introduction, produced water is generated during oil and gas production. In the United States, about 500 billion gallons of produced water are generated annually. And produced water is primarily disposed of through deep well injection, which is costly, has limited carrying capacity, and induces seismicity. Produced water reuse is vital to the environmental sustainability of the oil and gas industry and has many enriching benefits, such as providing an alternative water supply for industrial uses, irrigation, rangeland restoration, and stream augmentation. Removal of organic contaminants from produced water is crucial for safe reuse, since produced water is highly contaminated with organics from the oil and grease that it's been in contact with in the deep earth formations. And the issue, though, is that these contaminants are very difficult to remove using conventional methods, such as reverse osmosis, thermal distillation, or conventional oxidation processes, which are either too energy intensive or ineffective. And so photocatalysis offers a green technology that can effectively break down contaminants and produce water using photocatalysis and UV sunlight. So the hypothesis. During photocatalysis, electrons are excited to conduction band of the photocatalyst by ultraviolet light. This results in holes in the valence bond of photocatalysts from the electrons, which causes the electrons from the contaminants, from the organics, to fill these holes, which causes degradation over time. And these photocatalysts speed up this process and use UV light as an energy source. And so the organics in produced water are recalcitrant, which means they're difficult to break down. And so photocatalysts are very effective for this, where other treatment methods are not. And one issue, though, is that photocatalysis is only effective in the breakdown of dissolved organics and suspended particles. Though these organic particles can cause clouding, which reduces the effectiveness of photocatalysts since they require light. If the water is too cloudy, then it may cause the light to get absorbed into these other particles instead of the photocatalysts, which will slow down efficiency. And so the study hypothesizes that pretreatment to remove oil and grease and other suspended particles is necessary to ensure photocatalytic efficiency. Highly functional nanocomposite photocatalysts can utilize the full spectrum of solar energy with high photocatalytic oxidation capacity. And so the objectives of the study are to develop a suitable and environmentally friendly photocatalyst, to demonstrate the feasibility of those photocatalysts to degrade the dissolved organic contaminants in produced water. So for the methods, the produced water was first pretreated using settling, electrocoagulation, and cartridge filtration. And so this water was collected from the Permian Basin in New Mexico. And the photocatalysts were prepared two ways. One was just a pure titanium dioxide photocatalyst. The other was a gold-coated titanium nanoparticle photocatalyst, and that was prepared using an orichloric acid solution, which was then neutralized, or then placed in with the normal titanium dioxide photocatalyst, and then that acid was neutralized, which deposited the gold onto the photocatalysts. And so afterwards, we simply dried out the solution, and the cake of the gold deposited photocatalyst was created, and those were effective. And so the treatment efficiency of photocatalysts of the pure titanium dioxide and titanium dioxide gold was compared using the degradation of rhodamin B, which is a organic dye which is very commonly used to test the efficiency of organic degradation, and a filtered produced water solution. The experiments were carried out in a petri dish containing the photocatalysts, 5 grams to 1 liter of produced water, and irradiation using a UV lamp. So the degradation of organics was measured by total organic carbon, which is TOC, and it was analyzed using a UVV spectrometer. And so the photocatalysts were characterized by light absorption capacity, as can be seen here. The results are the nanocomposite particles of the photocatalysts are shown in figure 1, as you can see there, figure 1, which compares the non-deposited photocatalysts on the left and the titanium dioxide gold photocatalysts on the right. And here you can see a graph which shows the full wavelength scan using a UV spectrometer of pure TiO2, titanium dioxide, and titanium dioxide gold-coated photocatalysts. And as you can see, the line here at the top was the gold-coated titanium dioxide nanoparticle, and it has a higher light utilization efficiency and in the visible light spectrum, indicating a higher potential to utilize solar energy for water treatment as compared to the pure titanium dioxide photocatalyst, which is on this blue line here. And so figure 3 shows the removal organics by the nanocomposite particles of titanium dioxide gold without pretreatment. The TOC removal by the photocatalyst was about 4 to 5%, while the pretreatment was 59% of the total organic compounds were decomposed and mineralized into CO2 in 2 hours of UV radiation, which can be seen on this graph here, time hours, and the total removal rate. So for conclusions, the photocatalysis treatment mineralized about 59% of dissolved organic contaminants from produced water in 2 hours using titanium dioxide gold-coated nanoparticles as catalysts. Pretreatment to remove the oil and grease and suspended particles are necessary to ensure the efficiency of photocatalysts. And introducing gold to titanium dioxide nanoparticles is an effective approach to extend the visible light utilization efficiency of photocatalysts and increase their efficiency. And so the future work should focus on demonstrating photocatalytic efficiency and degrading a wide range of refractory organics using solar energy. And the implications and recommendations. Photocatalysis has demonstrated to be an effective treatment method for the degradation and mineralization of dissolved organic contaminants in produced water. It provides an innovative green technology using solar energy for the safe treatment and use of produced water in an alternative water source for industry and agriculture. And thank you to Dr. Pei Xu, my professor and advisor, and the master students, Tiloka and Chenling, as well as Kandan and Hayden Randall for sponsoring and running the Young Scholar program. Thank you for your time. This was my presentation on the photocatalytic degradation of organic contaminants in produced water. Thank you, and have a great day.